Martin. We'll have two speakers for this talk, and they will tell us about bootstrapping frustrated non-collinear magnets.
Okay, thank you. So yes, Martin and I are very glad today to have the opportunity to talk about this work that's been ongoing for a long time with him, Slava, and Balt. So maybe to give a brief outline of the talk, I'm going to start by introducing what are these frustrated non-collinear magnets. Frustrated magnets. It turns out that they have a very interesting phase transition that even though these models have been studied since pretty much the beginning of RG in the 70s, we still don't fully understand today. There's still some controversy in the phase transition. And then I'm going to let Martin speak about how we use the Bootstrap to try to resolve this controversy. Okay. For point one, here, we'll be interested in this interesting class of magnets that has a phase transition that is not of the usual ON universality class. And how we get this new universality class is by frustration. So in this large class of frustrated non-collinear magnets, there are two big subclasses. The first of the two are the so-called stacked triangular antiferromagnets. So for these, you get frustration from the geometry of the lattice. So you consider a usual antiferromagnetic nearest neighbor interaction, where you place spins on a simple hexagonal lattice, or a triangular lattice, as we could call it. And so let's say these are Ising spins. One component spins. Okay, this is too small.
Can you write a bit bigger?
Okay, let me write it a little bit bigger. So for one component spins, if we consider just one triangular subset, if I try to put one spin up here and anti-align this guy, then the remaining guy can't be anti-aligned with both. So the ground state will be degenerate, and it'll be either up or down. And for continuous spins, let's say just consider one triangle, then they will have this, the ground state will have this canted structure or non-collinear structure. And yes, so this will sort of relieve partially the frustration caused by the geometry of the lattice. So this is the first class. And the second class that will be part of the same universality class is Heli magnets.
Why is it stacked?
Okay, good point. So there I drew a two-dimensional lattice. To get the stacked part in 3 dimensions, just put these lattices one next to each other with whatever coupling between the lattices. It doesn't matter. If you put ferromagnetic coupling, then they will all be, it'll repeat the exact same pattern. And if you put anti-ferromagnetic, then it'll just alternate between 2 patterns. But so the frustration comes only from the interactions inside of planes.
And then the system is anisotropic then?
Yes, yes. Okay, and yes, we'll be interested. So there I'll draw 2-dimensional lattices, but the interesting question from the point of view of the phase transition is for these 3-dimensional systems. So for Heli magnets, let's say I draw a Heli magnet in 2 dimension, then in these you get frustration on the square lattice, um, not so. The lattice doesn't give you any frustration, but you consider competing interactions. So if you put nearest neighbor ferromagnetic interaction between all spins, and you add some anti-ferromagnetic coupling between next to nearest neighbors, only along one direction. This too. Okay. Sorry. And then some anti-ferromagnetic coupling along one direction. Say this is X and this is Y. Then along the Y direction. Then along the X direction, there's only the ferromagnetic coupling, so these will all be aligned. And because of this competition in the Y direction, it will start spinning like this. And the pattern repeats in the X direction. So, turns out that for both of these types of magnets, the phase transition between these interesting low energy states and the disordered states are part of the same universality class. And you can see this by going from both of these microscopic Hamiltonians to some that's probably still too small, to some effective descriptions for the critical modes. What you will get is some effective Hamiltonian in terms of a 2n component order parameter field, where the index A runs from 1 to n, where n is the number of spin components of the magnet, and I runs from 1 to 2. And this will be the most general effective Hamiltonian, including up to quartic terms, which is invariant under ON times O2 transformations. ON times big N, O2, symmetry. Where, okay, this transformation is sending phi AI to two independent rotations of the two indices. And so what will it look like? Well, there'll be the free part. And then for the quartic couplings, there are two combinations of 4 or 5 fields that we can make that will be invariant under these transformations. First one is if I contract the indices of the first two together. So this is something like phi squared squared. And the second one I get if I contract only the first index of the first two together. Phi bi, phi bj.
Sorry, okay. I didn't understand how this O2 appeared. How does this connect with your first board?
Yes, exactly. So what happens is that when going from here to here, you need to make a series of transformations. In particular, you'll need to transform from the lattice to momentum space and then expand around the minima of the Hamiltonian in momentum space. And for regular ferromagnets, there's only one minimum in this momentum space, and that gives one n-component spin. For these systems, there's two inequivalent minima, and that gives two n-component order parameters. And you can see physically what these represent. Let's say I write phi as let's say, so I write phi 1 as phi a1 and phi 2 as phi a2. You can reproduce this, okay, here, this pattern of the ground states. Now maybe I'm going to write something stupid, but you can reproduce this pattern as such. So the spins in this low energy state, you can write them as phi 1 times cosine of some special momentum. So the point is that phi 1 and phi 2 are the Fourier modes of the two special momenta plus and minus q star. And if you plug some phi 1 and phi 2 that are orthogonal here, you'll reproduce these ground states. And so the ON is the rotation of both phi 1s, and the O2 is the rotation of phi 1 and phi 2, which is just a change of phase in these cosines. Okay. And so in the literature, it's going to be more common to write it in the following way. So there'll be still the free part. And then some O2n invariant term. And then the following phi 2 squared minus phi 1 squared, phi 2 squared. Where, okay, I have already introduced what phi 1 and phi 2 are. So this makes clear that, okay, that there is this additional interesting coupling that breaks O2n invariance of the first guy into On times O2. And so the interesting question now is, well, from the experimental point of view, is to explain the phase transition of these magnets, but that translates into finding some stable fixed point of this effective Hamiltonian. And seeing whether there is such a stable fixed point in 3-dimension and for a physical number of spin components, n equals 2 or 3. Okay. So let me start. The second point, what is the controversy? Well, okay, first of all, from the experimental point of view, what people see is, first of all, is a picture a little bit more bigger. Yes, yes. Sorry about that. Hmm? Yes. Okay. Sure. That's not bad. Okay. So for experiments, what do people see? For lots of systems, you observe second-order phase transitions with exponents that separate into subfamilies. So there are many subgroups. No, that's still too small. Subgroups with where within these subgroups we observe the same critical exponents, but between these subgroups have different critical exponents. Okay, the second point is that in some of these subgroups, the critical exponent eta, which is related to the scaling dimension of the order parameter field, is negative. So this model is reflection positive. We would expect the CFT that describes its phase transition to be unitary, and this violates it. there are also in some of these subgroups violations of various scaling relations between exponents. And finally, for some, there is clear sign of weak first order behavior. So this sort of suggests a picture that's richer than for the standard phase transition of ON ferromagnets. It could be that there are multiple fixed points that explain the phase transitions of all of these subgroups. It could be that all of them are weakly first order if you go close enough to the transition point. Lots of these experiments are very old. The history dates back to the 70s, so it could be that with better experiments you could see first order behavior. So the picture is not clear. And unfortunately, okay, let's say this was I.
So can I ask you
Yes.
something more basic? So I suppose this is going to be in 3D, right? This
Yes,
theory.
yes.
But in your motivational pictures, the models were very anisotropic. So you expect this to be described by some isotropic field
Yes,
theory?
yes, that is the expectation.
Is there any simple argument for why this anisotropy is irrelevant? It doesn't.
It's a good question. I'm not sure. I'm not sure. Okay, let me move on to the theory part. So unfortunately, the different theoretical avenues they give different pictures of what should happen in 3D and for physical number of spin components. So first of all, could consider the epsilon expansion. In the epsilon expansion, if n is large enough for n larger than some critical value, you get the following RG flow diagram in the space of these two quartic couplings U and V. First of all, there's the Gaussian fixed point, which is unstable in both directions. Then along this V equals 0 axis, where V was the coupling that broke O2n invariance into On times O2, you find the O2n Wilson-Fisher fixed point, which I'll call H, which is stable in one direction and unstable in another. Then along some line here, I think it's V equals 4U. You find another unstable fixed point, stable in this direction and unstable in this direction, which I'll call C minus. And then here in the middle, where we have a stable fixed point up, which I'll call C plus, where its basin of attraction is this entire region here. So outside it flows to infinity, and inside it flows to this fixed point. And these are called C plus and C minus. C is for chiral. Because and supposedly this fixed point is the one which describes the phase transition of these magnets. And chiral, because these magnets have some chiral degree of freedom. If I look at the stacked triangular antiferromagnets, it has this sort of structure where there's a 120-degree angle between all the spins. You could either start rotating at 120 degrees to the left first, and then to the left again, or you could do it in the other direction, start turning right, and then you get something like this. So there are some chiral degrees of freedom, and this is why I called it C+. So in this picture, if n is large enough, there is a stable fixed point. And then as you lower n, these C plus and C minus get closer together. At exactly nc, they merge and they annihilate. And then for n below nc, only the Gaussian fixed point and the Heisenberg fixed point remain, and everything here flows away. So there's no stable fixed point anymore. And so from the picture, from the epsilon expansion, we only have to determine what this NC is. And if it's larger than 3, then we will expect that the phase transitions will be first order. And if it's smaller, then we'll expect that it's second order. And so we know this NC as some expansion in epsilon. It starts out large, starts out at 21.8, I think, with some large corrections. And okay, to now we know it to many orders, I think order epsilon 6. And this is, as is customary in the epsilon expansion, this is an asymptotic expansion. You have to use some tricks to resum it. And if you do so, for the largest order known in 3 dimensions, NC3, you expect something like 6. Maybe I should give, so it's pretty precisely determined to be 6. And actually, okay, you can, here, I'll leave this here. You can draw out the whole critical curve between 4D and 3D. Starts at 22 roughly, 6. Looks something like this. So this is the epsilon expansion. And so, okay, this is one way, one scheme to do RG. The problem is that in many other schemes that all fall under the so-called fixed dimensional schemes, get a very different picture. And okay, what are these? Well, in the epsilon expansion, you find fixed points perturbatively, so you'll have some beta functions, let's say for u, you'll have some epsilon part, and then the sum of terms, powers in u and v. And to find fixed points, you'll set this to 0 and find fixed points, say u star, as some expansion in epsilon. So to the n, and let's say u. And then to, for example, calculate critical exponents, you take your RG functions, let's say for eta. This you'll also have as some expansion in u and v. Plug the fixed point values, get some expansion in epsilon, and then resum it. So this is the epsilon expansion. And for fixed dimensional, for all these fixed dimensional schemes, you go directly to the dimension you're interested in. So there will be no epsilon. Have some beta, some expansion in u and v directly. And what you do is you resum the beta functions. So you'll have, let's say that will go into this, into some resum functions of u and v. And when you look for fixed points, say in 3D, you'll look directly for the zeros of this resum beta function. So there is an exchange of limits. In the epsilon expansion, you resum only at the end. in these fixed dimensional schemes, you resum first, and then when you want to compute critical exponents, you'll resum this series here and plug in the resummed values of the fixed point couplings. And what happens when you do this, and you look for where this solution of these resum beta functions. Ah, yes, that's true. Okay, let's say here fixed dimension is that these schemes agree with the epsilon expansion at first, but at some point they have some turnaround behavior, and then it's not clear what happens below. And this most usually happens for some d that's greater than 3. So in these schemes, you predict that all the phase transitions of these magnets for any spin components in 3D are second order. And actually, if you go far enough below this turnaround point, some value that's actually above 3, all of the fixed points that you find here, they have complex correction to scaling exponents. So these I'll call, let's see. So what you find from this is that at the fixed point, these corrections to scaling, which are related to the scaling dimensions of the subleading singlet scalars, these are complex, which again violates unitarity. It also violates, yes?
Sorry, I thought you said that for n greater. So I thought the whole point of NC was that for n greater than NC, you have real fixed points, and that was the definition of NC. And now you're saying that somehow the NC went down, like disappeared.
So I'm saying that these different schemes don't give coherent pictures. In the epsilon expansion, there's a nice.
Yeah, but then you're saying something about this fixed dimension scheme, right? And
yeah.
I thought the point of that plot was that NC kind of. Actually, I'm not sure what's the point of that.
The point, let's say for this curve, is that on the right side of it, there is no fixed point, and on the left side, there is a fixed point.
Okay, so but then I thought the idea was when you say there is a fixed point, there is a real fixed point. So why does it have complex dimensions?
This is a real fixed point. These corrections to scaling, the fact that they're complex, means that the fixed point is approached in a sort of spiral, but it is still at real couplings.
I see. And since I have the
Yeah, that's okay. Around here, these omegas become complex, but the fixed point is still found for real couplings.
Okay, thanks. And since I have the mic, can I also ask like a stupid question, which is, why do people think that these fixed dimension schemes make sense? Because the beta functions are scheme dependent, and then you like take something arbitrary and you start resumming it. Like this doesn't seem to make much sense.
I agree, and in particular, I was going to talk about the fact that. That we generally expect that these beta functions look like gradient flow. So what means that we expect that the beta functions in these types of models, they have the form of some metric times the derivative of some potential. So this is known in perturbation theory for a certain amount of loops, and we expect this to be true non-perturbatively. And if you do so, well, flows that respect this shouldn't have fixed points that spiral inwards. But there are many reasons to doubt.
The more basic problem, which is that this beta v that you're resumming is like depends on the scheme in the sense like of how you regularize things.
Yes.
And subtract divergences, and then you're trying to resum that, which is ambiguous.
Yes.
So people still think that this somehow makes sense?
I think people can still control, for example, the large order behavior, and so they still have some trust that if they stay within some fixed region, that they should at least be able to resum them.
Sorry, can I ask, what does it mean to have two values of NC in a fixed dimension?
This means that, well, yeah, for example, here,
Yeah.
what happens here is that for n large, here you have some real fixed point with some real corrections to scaling. These people find is that when you go below it, some fixed point reappears that's not connected to the one above, but that is still stable. And these are the fixed points that have these complex
So the fixed
corrections
points
to
now
scaling.
exist above and below.
And below, exactly. Yes. N should be either 2 or 3, yeah. Okay, so I think that's about what I wanted to say. We see now that from the experiments, it's not clear what should happen, and also theory doesn't give a coherent picture, and now we would like to use the Bootstrap to plot this NC curve and see which scenario is correct. So now I'll leave it to Martin. Yes?
Thanks. I have a question. So is your fixed dimension scheme the same as larger expansion or different?
Is the same as what?
Unit larger expansion.
No, no, no. For example, for one of these schemes, you use the same MS bar scheme that you use for the epsilon expansion, and you just plug epsilon equals 1 if you want 3D, and then you resum this.
Okay, then could you comment about the larger expansion result about the critical?
Yes. So what happens is that in the epsilon expansion, okay, let me see. One thing that we know to happen when two fixed points get closer together is that, when they merge and annihilate, is that a lot of the CFT data will depend, so let's say for scaling dimensions, they'll have some square root dependence. And in the epsilon expansion, you see that something like square root of n minus nc4. You see these pop up everywhere in the CFT data near nc. And at large n, you don't see that. At large n, well, you know that if n is large enough, the fixed point always exists. So the large n expansion is sort of oblivious to nc. One thing you can do is take the large n data, let's say for the leading irrelevant singlet. So this will have some expansion. It'll look like 4 minus some order 1 over n correction. And you can check when this quantity crosses marginality. So that's one way to determine NC. But it's a little less natural because, in fact, the large n expansion doesn't really see the merger of the fixed points.
I mean, forget about the major scenario. Just is there any prediction about the critical n from large expansion?
Yeah. I think
So
I don't know it by heart, but it's above 3 also.
It's about 3. How about the compare? Is it close to 6 or 5.9?
I don't remember, unfortunately. But this large n expansion is not known to many orders. It's much harder than the epsilon expansion, so it would be less reliable.
Yeah, my point is that because the NC could be a little bit big, like if it is close to 6, then probably the large expansion could make sense. Of course, if you cannot see the skinning of the skinning of the skin dimension near the critical NC, but that's another issue, right?
Yeah, I agree. But still, even if I agree with you that this NC that you expect to find from the epsilon expansion, it's large. Still, the large n expansion is not the most reliable way to see this, because the true mechanism is this merger of fixed points, and you can't see it there. So you can only really, here large n should be understood as not just n large, but n much larger than nc.
Okay, thanks.
Okay.
So now that Benoit is motivated us all that this is an important problem to solve, I will talk about how the numerical conformal bootstrap can help us solve this controversy. Um, so I'll be talking about what numerics can do for us in this question. So what can we expect the Bootstrap, the numerical conformal Bootstrap to tell us? Well, we would like it to tell us to find this NC, where this chiral ON cross O2 CFT C plus stops existing. And it would also be great if we can find some evidence for the mechanism by which it disappears. Okay, well, whatever. Which is expected to be this merger with the antichiral fixed point followed by an annihilation. Moving, the CFT is moving off in the complex plane. So, to answer these questions, well, if we want to find this NC, how could we do that? So one way to do it would be to find an island, as we are used to in the Bootstrap, for some value of n above NC. For n. And to then follow it down. Until it disappears. So, to do this, we will be studying a system of correlators of the bifundamental and the first singlet, which has been studied before by Hendriksen, Koesvoets, and Sterjoe. And so, well, we will be looking for an island, and we will be using, in order to find this, we're using the navigator method, which I won't explain in full since it's been presented before, but the idea is that we previously, when you looked for an island, you could test points, but if you didn't find allowed points, you had no idea where to go for disallowed points. Now there is some function that gives you a measure of success, and if I check this disallowed point, I will get an idea of how far I am from the allowed point, and its gradient will tell me where to go. So this will allow us also to search from slightly higher dimensional spaces, which will be very useful. We'll also be using the new skydiving algorithm developed by Liu, David Simmons-Duffet, Ning Su, and Balt van Rees, which is basically, I won't explain it because it's of course not mine to explain, and I think we'll get a presentation on it next week. But the idea is that you move in both in the internal SPV parameter space and in the external parameter space to even more efficiently search for the island. So finding an island for this CFT is not that easy. And it's one of the CFTs where it's a bit more difficult. And why is it more difficult? It's because it doesn't live at the kink in a singlet bound. Because there's another theory that lives there. In this case, it's this the enhanced symmetry O2n, the O2n symmetric CFT. So we have to find out what we need to know in order to find this isolated island first. So we'll bootstrap this system. So we have some OPEs. This will exchange, I will use the notation R prime, where R will denote the ON representation and R prime the O2 representation. And this will exchange here R, R prime, R out of S, T, and A. And of course, you have this bifundamental exchanging with the singlet, exchanges the bifundamental itself, which I denote by VV. And of course, S cross S exchanges singlets. Now, what do we need to know in order to first obtain some island at some value of n greater than nc? Well, what do we know about this theory? One thing we of course know is that this is the stable fixed point, so there's only one relevant singlet. And we might hope that this is enough to get us an island. Also because you might think that this is enough to exclude the Heisenberg fixed point, because it has this additional ON cross O2 relevant singlet. But if you look carefully at what this operator is, in terms of so we know that at this enhanced symmetry point, the representation, the operators fall into representations of O2n, which means that there's actually an enhanced symmetry and there's additional symmetry selection rules. So specifically, this operator comes from, in the O2n language, if you take this operator, let's write this O2n vector that you can construct from our O2 ON cross O2 vectors like this, then this operator comes from a contraction of a 4-index symmetric tensor and because of this enhanced symmetry, you can see that its OP coefficients, let's call this F for 4-index symmetric, that by symmetry this has to be 0. And the same holds for all the other OPEs that appear in our bootstrap. So we are actually insensitive to this operator. So we will need something slightly more. No, okay, maybe this would be nice to keep.
So you would see it if you use as external operators one of these symmetric.
So you would need to be, for example, use the traceless symmetric of yeah, because you need to have enough indices to contract these down. So phi can't exchange F, but TT would be able to traceless symmetric. With traceless symmetric would be able to exchange this operator. But that would become quite an enormous bootstrap equation. So we will see that it's not necessary to go there. So because what more do we know about these theories? One thing that we know, basically this search for NC will take place at relatively large values of NC, and definitely at relatively large values of where 2n is relatively large. So it will be good for inspiration to look at what we know at large n. So at large n, some things happen. One, we can first look at O2n, and we get that this phi squared gets replaced by a Hilbert-Stefanovic field that has, at first order, a fixed dimension, dimension that doesn't depend on the dimension of spacetime of 2. Now in ON cross O2, the same happens, But also, if you take an anti-symmetric tensor of O2, then that will give you a similar field that has a fixed dimension of 2 plus order 1 over n. So this tells us a few things. One is that there are certain large gaps expected in certain sectors. So for example, if you take the stress tensor, then there's expected to be a gap of 2 above this. Similarly, if you take currents, there's again expected to be a gap of 2 above these. If you take phi, there's expected to be again a large gap. So what we will phi above it. So we will be assuming that there's a gap here of 1 to be conservative, to leave room for perturbation theory to not be for large n not be exact. And the same for the currents, which here are the AS and as the first operators in the AS and SA representations. We expect that there is a gap above these again of at least 1, that this is very conservative. And for delta phi, we will be assuming that there is the second operator is larger than d minus 2, which again, all of this holds in epsilon expansion, all of this holds in large n by quite some margin. So all of this is expected to be completely reasonable. Sorry, delta phi prime. So there is, or in this language that I wrote before, the phi, if the VV, this the bifundamental, that there is a gap above this. Now, and all of these have a large margin with both epsilon expansion and large n. Now we can look what we get if we assume this, for example, in the space of delta S, delta phi. And we see that it isn't quite enough. We get some large allowed space, which contains the O2n or H fixed point and the C plus fixed point. For good question, what am I drawing? So let's start by drawing the case g equals 3.8 because we know where the theories are and it will be a good reference before we move to d equals 3 where we're really interested in, and for n equals 20, some value a bit above the expected NC value. So we need something more. So we can look again at what we know from large n to see whether we can see the differences between this O2n fixed point and the C plus fixed point. And there's a clear difference in this fact, that in this ON cross O2 you have this additional Herbert-Stefanowicz traces symmetric field that has this fixed dimension. And so we will see that it's very interesting to look at this channel for differences between these theories. So let's say that we draw for D here. So we see that already in this first operator there is a big difference because this has this 2/0th order fixed value of 2. So here I write delta ST in C plus, and here I write delta ST in H. Whereas these other one will go down as we lower D. And also, you see a repeating pattern you can compute in large n for the next operator. You basically see a repeating pattern that this one will stick out above the other. So one thing that you could now want to do is to put a gap assumption here and add delta ST to the variables that we scan over the first operator in this channel. But that would require quite a lot of faith in the exact perturbative results that you computed. So we find that it's not required to do that. We can just put a gap much lower, still scan over one operator, This assumption doesn't exclude H, so we might think that that's a problem, but it is not, because what we find is that we get a nice isolated island here, and then okay, let me write boxes because we use navigator to determine extremes, and we find an isolated island here. We also, I should say, find perhaps slightly unexpectedly another isolated island, which corresponds to the anti-chiral fixed point. So it turns out this anti-chiral fixed point, it's the unstable fixed point. It has a singlet that is an extra relevant singlet, but it's close. We're close to NC, and we know that it's going to approach marginality at n equals NC. So you have this extra relevant operator, but it's high up in the spectrum, and it turns out that our bootstrap is not that sensitive to the exact location of this second operator, so whether it's slightly above marginality or slightly below. So this fixed point, this island also survives. So this is what we get here in d equals 3.8. Now, of course, we want to see what happens in the case where we're really interested in, which is d equals 3. And in this case, we go again to some n a bit above criticality, the critical n. And we see that we again nicely get a small isolated island for the O2n fixed point, and we get this time a bit bigger. Island for the C plus fixed point. And we find the navigator minimum very close to this prediction. This, of course, you need to use a resummed epsilon expansion in order to get accurate results for this prediction by epsilon expansion. This time we don't find a second isolated island. The prediction for C minus by epsilon expansion is a little bit below our island, so it could be that we're now sensitive enough to exclude it. We didn't find any second minimum, so there wasn't really an evidence for finding this island. So it could be that we're just sensitive enough to exclude it, or it could be that the perturbative correction is a bit wrong and it lives at the bottom of this island. For what we're going to do, it doesn't matter, because what do we want to do now? This is at lambda equals 39. Sorry, lambda equals 31, but I checked. Yeah, this is at lambda equals 31. And here all these islands are stable until lambda equals 43. Sorry, the question was whether I found, when building up in lambda, whether I found a dagger shape.
Yeah, I'm just wondering if it's some analogous story to what we saw in the POTS model, because I mean, I guess we've only done lower lambda so far, and there we only got a dagger.
So what I remember, I guess it was different. From what I remember, in this case, in d equals 3.8, I remember that there was a point at lower lambda where these two islands were not separate, and then they become separate, isolated islands. That's something I remember as you progressed in lambda. I think that here, I think that here, if you lower lambda, the problem is that you get a connection between these islands. I don't know whether you mean this by a dagger shape.
Well, I just meant like the setup you're using to find a specific theory. If at sufficiently low lambda, you find that the theory in the space of, say, 3 CFD data would appear at the point of an allowed region. Because, I mean, when we were, I guess, looking at the analogous phenomenon for the POTS model, also looking at merger annihilation, that's what we found. So I'm wondering if it's something kind of generic to this phenomenon, or something peculiar to our case, and you didn't see this in your case.
Yeah, so I would go more in the direction that it probably is something peculiar about your situation. That POTS model. So Yeah, I don't remember. I think that we started already with lambda equals 19 as the lowest value, and I think that here in d equals 3, I remember best. Here you already get the isolated island, but you get that they are together. I think here you get that these merge, and perhaps also that there's a connection to the peninsula at lower.
No question. So did you use the same gaps for d equal to 3 and d equal to 3.8?
So yes. So no, I would say sorry. We use this. So delta unitarity obviously depends on the dimension of the spacetime, and here we use d minus 2, and so this is the this is d over 2 plus 3 else. Right.
You mean that's in 3D? Right.
Sorry?
That's the gap you use in 3D? Or?
No, this is what we use. This is this line, d over 2 plus 3 else.
So are you worried that because the C minus is outside of your island slightly, is it possible that you introduce some gap that is slightly above the physical value so that you excluded the C minus solution?
So, first of the C minus, of course, it should be excluded already by the singlet.
But you mentioned that the singlet constraint doesn't work, be.
Whether our constraint excludes any of the other, I think not. I think that C minus will also be up here with the others, so it will not be excluded in this channel.
Yeah, I think my question is that in 3D for n equal to 8, is it possible that, or are you quite sure that the extra assumption given by this read dash 9 are physical, or?
Sorry, I didn't hear the last few words. Sorry.
Okay, in 3D,
yes.
The gap assumption given by this red dash 9, are you sure that they're physical, or?
Are you wondering whether perhaps this operator goes all the way below this?
No, I'm not quite sure. I don't know the numerical values, so I'm not quite sure. I'm asking you if you are sure that all the gap assumptions you introduce.
Yeah, I mean, I would say that I'm sure. I think we have like a safe margin with any large n or epsilon prediction, and also I can mention it later. There's basically independent evidence that this goes a bit ahead of what I wanted to do, but you can also ask the question. So we're going to find some critical n, which is now running a little bit ahead, and you can ask how that depends on this gap. And so this is a bit work in progress, but roughly we find that there is a kind of a range where it slowly linearly increases, and then there is a range where if you of course go too high, let's say that this is the perturbative direction prediction of this operator in C+. If you go too high, then of course you start just excluding the whole theory, and so this goes away. And so we are basically at this end where we do the most conservative gap assumption that is very safe. But I think that this is additional evidence that basically in this region where it's slowly increasing, that the perturbative estimate is probably correct, that it lives somewhere here, and that we are quite a bit below it.
Can you tell us what's the y-axis scale? What's the numerical value correspond to the transition
Here?
point?
How much this will differ?
Yeah.
Like 0.5.
Okay, thanks.
So I ran a bit ahead. So what we were going to do, so we found an island. And now we want to follow it down. So let's put that plot flat and add an extra dimension. An extra axis, which is n. So we have this island, we have this island. Now we want to move down in n. Now we know that for this, we have this Heisenberg O2n fixed point, and we have this chiral fixed point. For this one we know, I mean, it's going to move, but it's going to keep existing. But here, it's going to move, but then it's just stops at some critical NC. And so what we're going to do is use the navigator to walk there. And so, yeah, we can now, so you start from the correct fixed point, and then you find the correct endpoint of the theory. And so if we do this, I guess I can also just draw it in here. We can do this for all these values of d. And we get something that goes to, under these conservative assumptions, it goes to 3.78. And so we see that it firmly excludes this possibility of a turnaround, and it's well above 3, so we clearly can conclude that there is no chiral O2 cross O2 or O3 cross O2 CFT. And so we can conclude that there's no second order phase transition in non-collinear magnets. Sorry? And yeah, so that's basically what we wanted to do, and we've done it. Then we can also ask one question we had, can we see evidence for why this happens? I mean, we expected this merger annihilation. So we can look, and this merger annihilation has various signatures, but one signature is that the CFT data, maybe I should have. Data will depend on, will go as square root n minus nc. And you can in principle see this in various data, but the one that is clearest for us, also because we have a decent precision on it, is if we plot the dimension of the first singlet for various values of n, then we see that this follows a nice square root. And in fact, as we increase lambda, it gets closer and closer to like a perfect square root.
I thought this behavior was just close to NC, right?
Yeah, so sorry. So here you're saying why it is in such a wide range, all the way from
yes.
30. Sorry, I should say this specific plot is in d equals 3.8. You might also wonder, okay, but if it's first I should, like, isn't that still in the perturbative region? How much does that say? But one thing that you should note is that in the epsilon expansion, the thing that you find is a square root n minus nc, which would be a completely wrong prediction, because of course you need, what we find perturbatively is that you get n minus nc. What do I want to say? I want d, just the correct d. Yeah, you say why is it in such a there's an analytic part. There's something plus square root. Sorry?
So there's something that in front of the score that should be the space-time dimension, right? That's the marginality condition, right? For the data S. Yeah, the number just write down.
Yes.
So the general formula should be the space-time dimension plus some number times square n minus nc, right?
No, I mean it can be something more complicated.
I mean, for the singlet operator, it should be the
this is not the
space-time.
marginal. This is the first singlet.
Oh, that's the first singlet. Okay.
It's not the singlet that becomes marginal.
Okay. But it's still like that. George just asked it. I mean, that formula just obtained from the conformal perturbation theory, right? It is supposed to work only near the critical NC. I mean, it does. It's a bit weird that it works even for n equal to about like a 22 or even higher. So do you have any explanation?
I don't know.
about
We
this?
know also it has to approach at large n, of course, too, which might also restrict how it can. Yes. Yes. Okay. Yeah.
Do you have similar result for the second singlet operator, which cross marginality condition?
So
Yeah.
no, as we also see from the fact that we didn't exclude this, is that we don't have that high an accuracy on the determination of the second singlet. So yeah, there's let me conclude with there. So there's various things that might still be able to improve. So one is that it would be nice to do this, to see this for the operator that becomes exactly marginal. Another thing is, well, you might wonder why our bound, which is a lower bound, so I mean it's consistent, but why it's not closer to, for example, this epsilon expansion. It could be that this epsilon expansion, there are multiple resummations, is somewhat off, but it could also be that we are not that strong yet, that we are that close to the actual bound. So both to so one way to get slightly higher bound is to make your assumptions more stringent, which basically I talked about already. You could put, instead of the gap here, you put it here. You have quite some evidence that that's correct, and you would get it a little bit higher. You're still not going to get to 6. So another thing to do things like get a stronger bound here and be able to do this for the marginal, the operator becomes marginal, would be, of course, to setup. So you could do, for example, the second singlet, or you could add this ST operator that we see that is important, and that might be able to resolve these things. Another thing that would be nice if you could do it here, also to solve the problem of whether the epsilon expansion is off or whether our bound is just not strong enough, would be nice if we could both get an upper and lower bound. Now, the lower bound is a very intuitive question by the CFT because you're just asking whether the CFT exists, and it's a logical question to ask whether you can exclude it. But you can actually also, at least in principle, also get an upper bound, because you would do that by demanding that delta S prime is exactly 3, and then put some gap above that. That should only be allowed in the vicinity of this NC. And so we should be able to look by using that and get both an upper and a lower bound and maybe get more string. But why can't we do this now? It's again the problem that we encountered, that we are not that sensitive to this operator. But again, I think in principle for a future study, all of these problems might be solvable, and you might be at both an upper and a lower bound and stringent by adding, for example, one more operator. Ah shit, this is in 3 dimension. Yes, I mean, of course, equals D. Thank you. I think that was, I think I...
Any more questions? For Martin or Benoit?
Thanks. So one question is that you said you can get the O2 in Ireland based on your site setup, right? So you just start from the O2 course ON by fundamental, Skinner 4-point correlator, and also in the mixing correlator system. So you can get the O2 in Ireland. Is that that's true, right?
Yes.
So I mean, it's a little weird because you already impose a gap in the AS bar and the SA bar sector, which is above the unity band. Above the unity band. So
that of course holds in both theories.
Sorry?
That holds in both theories.
But in O2 in wicked model, that's not true, right? in the O2 vector model, if you branch the O2n spin 1 operator into the O2 cross ON sectors, there will be a conserved current in the AS bar sector as
No,
well.
no, no. It will be in the in the
There is, we assume that these guys exist, that there is a stress tensor, there are these two conserved currents, and then gap.
yeah, yes.
Yeah, I mean for the O2n, there's the only first of
So there will be. Yeah, sorry. So I think so we have this current of O2n, which goes into both like the AS and the SA current.
yes.
I mean, we assume that these are there in both theories.
Or you impose
we-
that there's already a conserved current in that sector, right? Okay.
So sorry, are you now do you agree? So this one is both there in the O2n theory and in the ON cross O2, and we just assume it's there, and then we assume a gap above that. Maybe
Okay.
I should have been more clear when I said this. Of course, we're not saying that there's no current, because there is.
Then, okay, that explains my question. Thanks.
Any other question? Okay, so if not, let's thank Martin and Benoit.